Okay, this is project test 6, video number 2, problems 11 through 20. Ecologists wanted to estimate the mean biomass of a certain forested region. Ecologists divided the region into plots measuring 1 square meter each, and they selected a random sample of 9 plots, so we have n equals 9. The mean biomass of the 9 plots was 4.3 kilograms per square, and the standard deviation was 1.5. So we have an X bar equal to 4.3 and a standard deviation of the sample of 1.5. Assuming all conditions for inference are met, which of the following is a 95% confidence interval for the biomass? So first off, this is going to be a t distribution since I'm using the standard deviation of the sample. My formula is going to be as follows: x bar plus or minus t star s divided by the square root of n. Well, here we are going to have 4.3 plus or minus. We'll come back to t star in just a moment. S is going to be 1.5 divided by the square root of 9. So we're going to go calculate t star real quickly. Second vars, inverse t, parenthesis 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom in this case, we had a sample size 9, so my degrees of freedom are 9 minus 1 are just 8. And we end up getting 2.306 for our t star. So real quickly, I go, you know what? That gets rid of these first two. All right. And I'm going to come back to those in just a moment. We all have 4.3 down. That's good. We have 1.5. This one's wrong because it has a square root above it. Then we have here the square root of 9. Be careful. The square root of 9 is just 3. So we could have written 4.3 plus or minus 2.306, 1.5 divided by 3. And consequently, our answer is choice E. Now, the only reason I took the square root of 9 is because it's easy, and I'm sure they thought they could trick you and get you to mark this one incorrectly. Okay, so that's so the answer to 11 is E. Now, I real quickly wanted to change this up. Had this been the standard deviation of the population, it would have been X bar plus or minus Z star standard deviation divided by square root of n. So then we're going to be changing what we're doing here, but that's not what we had. This is what we had, okay? And had we used the Z star, we would have gotten 1.96. So that's how they trick you. All right, so that's number 11. Number 12. Staff members of a high school newspaper wanted to obtain an estimate of the average number of years teachers in the state have been teaching at an educational conference attended by many teachers in the state. So they went to an educational conference. The staff members randomly selected 50 conference attendees and asked the attendees how long they had been teaching. Which of the following describes the sample and the populations to which it most reasonable for the staff members to generalize the result? The sample is the 50 conference attendees. That much is true. So we can get rid of the sample is all, the sample is all, and this. So the sample is the 50 conference attendees. The question is, who's the population? All right, now what they wanted was the population for all teachers in the state. But in fact, we only selected them not from the state, but only from conference attendees. So our population is the conference attendees because we selected from the group of conference attendees. To have done this, they would have to take a random sample of the entire state of teachers, okay, or some other sampling technique. But they only selected from conference attendees, so we can only apply it to conference attendees. All right, number 13. Grain moisture is a characteristic of grain that affects the price paid for the grain. A random sample of 28 loads of corn was evaluated for moisture as percent of the total weight. A different random sample of 28 loads of soybean was also evaluated for moisture. The data are displayed in the box dot plots below. Based on the dot plots, which of the following is the greater for the percent moisture of corn than for the percent moisture of soybean? So we want corn to be greater than soybean for whatever we're looking at. All right, so they asked for the first quartile. Well, I'm going to come back to these because when they have problems like these, I look to see if there's anything that's obvious first, just because it makes my life easier. But I am going to come back and address the other points. Well, I look at this and I go, you know what? Corn is more spread out than soybean. So corn is going to have a larger range. So my answer choice is D. Corn has a larger range. Basically, 20%, 0.20 minus 0.06 is 14%, where this is going to be 19% minus 8%. I guess that should have been a 7%. That should have been a 7. And 20 minus 0.17, 0.13. And this is going to be 0.19 minus 0.08 equals 0.11. So this is corn. This is soybean. Obviously, corn has the larger range. And I can just look at the drawing and figure that out. The first quartile, had I wanted to do that, I could have gone, you know what? The first quartile, each sample is size 28. 28 divided by 7, 28 divided by 4, because the quartile is 4, equals 7. So my first quartile for corn, 1, 2, 3, 4, 5, 6, 7. So it's going to occur right here at 11%. That'd be my first Q1. I could have done the same thing for soybeans. 1, 2, 3, 4, 5, 6, 7. Q1, same spot. The median, that's going to be 7 more, or at 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's going to occur right there between 14 and 15. So this is going to be my median. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Occurring right here. Once again, this is the same spot. So real quickly, I could have done all that work, but it's much easier, I think, to go, you know what, corn's more spread out. Obviously, if it's more spread out, it has a larger range. That's one of the answer choices. I'm stopping there, okay? All right, number 14. A sleep time of 15.9 hours per day for a newborn baby is at the 10th percentile of the distribution of sleep times for all newborn babies. Assuming the distribution is normal with a standard deviation of 0.5, what is the mean sleep time? So here's what we have. We happen to have an unknown mean. We do have a standard deviation of the population of 0.5. And we know that a sleep time of 15.9 hours is associated with the 10th percentile, or 0.10. So if I write down my Z formula, Z equals X minus mu over sigma, I can start plugging in to see what I have, all right? So if I want to see what I have, and if I want to see what I have, it's like, well, I have an X value, 15.9. We know we don't have a mean. We have a standard deviation of 0.5. So I'm hung up here with, can I get a Z-score? And because they gave me the area, I can go ahead and do that. Second vars, inverse norm, area is 0.1, mean is 0 because it's a Z-score, standard deviation of 1. And I end up getting negative 1.28. At which point I can go ahead and solve this thing. So I'm going to multiply by 0.5 times 0.5. and I'm going to subtract the 15.9. When I do that, I get a negative 16.54 equals a negative m. Make both sides positive. My closest answer is D, and 14 actually is D. All right, moving on to 15. As part of a science experiment, a student recorded 10 measurements of the temperature of a liquid. One of the measurements was an outlier when compared with the other 9 measurements. Which of the following must be true about the 9 measurements excluding the outlier when compared with the 10 measurements? Now, one thing they said is an outlier, but we don't know if the outlier is on the high side or low side. We just know that there's an outlier, okay? So the median of the 9 measurements is less than the median of the 10 measurements. Well, medians are not typically impacted by outliers, so we don't know that there was a change. There might have been, we're not necessarily sure. Again, this next one is addressing median. Median's typically not impacted by outliers, so we can ignore that. The maximum of the 9 measurements is less than the maximum of the 10 measurements. Maybe, but what if the outlier was on the low side? If the outlier was on the low side, then the maximum didn't change. In other words, if I had a dot plot, a box plot that looked something like this for my 10 measurements, and my 9 measurements now looks like, so losing that outlier does not impact the max, or might not. We don't know, and it's supposed to be, it has to impact the max. The maximum of the 9 measurements is greater than the maximum of the 10 measurements. Well, if this is the 10 and this is the 9, it's possible that that could happen, but not assured. And because it's not assured, we don't know. What we do know is the 10 is more spread out than the 9. And if the 10 are more spread out, the 10 will have a larger standard deviation than 9. So the standard deviation of the 9 is less than that of the 10. And the reason is because the standard deviation formula, once again, and this is conceptual, is the summation of x minus mu squared over n. And if I get rid of the one that's a long way away, this distance gets smaller. So as I get closer to the mean, my standard deviation gets smaller. So consequently, removing an outlier makes me have a smaller standard deviation. 15 is E. All right, on to problem 16. At a local ice cream store, 210 people were surveyed on whether they preferred eating ice cream from the cone. Of the 210 people surveyed, 70 were adults and 40 were children. Of the responses, 150 indicated they preferred the cone. So 150 out of 210 preferred cone. All right. For those surveyed, there was no association. In other words, they're independent between age and preferred. Which of the following shows the distribution of the responses? Remember, if there's no association or if they are independent, and remember, no association means independent. And because they're independent, they are proportional. So I can set up a proportion to solve this problem. So we have 150 who preferred cones. Well, we had 70 adults. So if I solve that, that's supposed to be an A. So if I have 150 times 70 divided by the 210, I go, you know what? 50 adults prefer cones. All right, so I need to find one that has 50 adults preferring cones, and that's right here. 50 adults out of 70 preferred cones. But I could check it out with the children. So 150 out of 210 preferred the cones, and we have 140 kids. 150 times 140 divided by 210 equals 100 kids preferred the cones. And sure enough, that's what we have here. 100 children preferred the cones, 100 out of 140. This is a proportional 50 over 70, 100 over 140, 150 over 210. All right, so that takes care of question number 16. Number 17, a two-sided t-test for a population mean is conducted of the null hypothesis mu equals 100. Well, if they're telling us HO mu equals 100, then the alternative, since it's two tails, is going to look like that. If a 90% confident t-interval constructed from the sample data contains the value of 100, which of the following can be concluded about the test at a significance level of alpha equal 0.10? So they're saying, hey, you know what? We're going to construct a confidence interval. And here's their confidence interval, and they constructed a 90% confidence interval, 0.90, and alpha equals 0.10, because the area in this tail is 0.05 and the area in this tail is 0.05, and alpha is the area in the tails, and this is the rejection region. But as it turns out, I don't know where it occurred, but somehow 100 is contained in the interval. So it's not in the rejection region, all right? So that tells us about the hypothesis test, all right? If we're not rejecting because it's contained, then the p-value can't be less, it must be greater because it was contained. So the p-value is greater than 0.10 and HO should be rejected. That's false. If it's greater, it should not be rejected. All right. So our p, because it was contained, then our p-value must be greater than 0.10. In other words, it wasn't in these rejection zones, and it should not be rejected. All right. We failed to reject when our p-value is greater. An agriculturalist working with Australian pine trees wanted to investigate the relationship between the age and height of an Australian pine. A random sample of Australian pine trees was selected, and the age in years and the height in meters was recorded for each tree in the sample. Based on the recorded data, the agriculturalist created the following regression equation to predict the height in meters of the Australian pine. So what we have here, remember, age is, this is going to be my X variable, this is my Y. So we're going to have height over age. And we're going to have a 0.48, a positive 0.48 height for every 1 year change in age. So the height increases on average by 1 meter. Nope. The height increases on average by 0.48 for each year, for every 1 year change in age. And so our best answer to number 18 is B. All right. And it really does help if you go back to the Algebra 1 skills and just make the fraction. And this is our X, this is my Y. So my height is my Y, my age is my X. And so in the denominator will be, unless it's a special circumstance, will always be 1. So 0.48 over 1. So there's a positive 0.48 increase in height for every 1 year age increase. Number 19. At a certain store, the distribution of weights of cartons of large eggs is approximately normal, with a mean of 26 ounces. Based on the distribution, which of the following intervals will contain the greatest proportion of cartons of large eggs at the store? This is a type of problem that shows up every few years. Not a difficult problem at all. And basically, we have 26, 28, 30, 32, and going this way, 24, 22, 20, 18, etc. All right. The center has the greatest proportion of values because we can see that because it's taller, even though the number line on the bottom is the same. Well, when I look at this, this is 20 to 40, 24 ounces. That's 4 ounces. That's 4 ounces. This is 4 ounces. This is 4 ounces. And this is 4 ounces. So all of these have a horizontal distance of 4 ounces. 24 minus 20, 26 minus 22, etc. So the one that's going to have the greatest is the one that's centered on the mean. And 24 to 28 is centered on the mean. Therefore, 19 is C. It'll have the greatest proportion. And why? It's because the graph or the normal curve is taller in the center. Number 20. In 1960, sociologists studied a random sample of 1,018 families that consisted of a husband and a wife and at least one child. Of those families, 5.8% reported that the wife was the primary wage earner of the family. In 2011, the study was replicated with a random sample of 1,013 that the families that consisted of a husband and wife and at least one child. Of those families, 22.3% reported that the wife was the primary wage earner. So 1960 is 5.8, 2011 is 22.3. Which of the following represents a 99% confidence interval for the difference between the proportions of the families that consisted of a husband and wife and at least one child from 1960 to 2011? Well, all right, first off, let's write down our formula. P hat 1 minus P hat 2 plus or minus. And remember, every time you're working with a proportion, it's always a Z. So this is a Z star. P hat 1, Q hat 1, N1 plus P hat 2, Q hat 2, N2. All right, so we notice that they're calling P hat 1 0.223. So 0.223 oops, 0.21 minus 0.223 equals 0.77. So there's where the 77 comes from. All right. And then we have 0.058, 1 minus 0.058, and we end up getting 0.942. So we're looking at these problems and are like, okay, which ones look possible? This one doesn't match. These don't match. I'll address those in just a moment. But these do, because we have the 223 and a 77, the 0.058, 0.942. So all of those have this correctly. The only thing we're going to have to worry about is this Z star. Well, Z star is going to be second vars, inverse norm, parenthesis 1 minus 0.99, close parenthesis, divided by 2, mean is 0, standard deviation of 1, and we end up getting a 2.576 as our Z star. So consequently, C is our answer because this is the Z star that we were looking for. Now, these problems are actually important to us. They're not based on this formula, and we were supposed to be using a confidence interval. Had they asked us to use a hypothesis test, we would have had this formula, P hat 1 minus P hat 2 over P combined, Q combined, N1 plus P combined, Q combined, N2. And we would need to calculate P combined, and P combined, or P hat combined, equals X1 plus X2 over N1 plus N2. So once again, be careful. Confidence interval is going to be P hat 1, Q hat 1. Hypothesis test, P hat combined, Q hat combined. Make sure you make the distinction and you're careful with that. All right, that's number 20, and we'll move on to the next video. Thank you.